Hello, my name is Eddy Wan, and my mentor is Robert McGillivray, and this is my project, the Autonomous Robotic Lawnmower. So in this presentation, I'll be going over my introduction, my engineering goal, my methodology, results, conclusions, future research, acknowledgements, references, and then I'll open the floor to some questions. So I based my project upon a commercial robotic lawnmower called the Artomower, which can be purchased from a company called Meritronics. So it comes in a kit. This kit would consist of a chassis, sensors, a perimeter wire, and an Arduino board, which is used to control the robot. So the reason that you may want a robotic lawnmower is that, say, in the summer months and you need to mow your lawn, if you did it yourself, you'd be out there in the heat and it would take a lot of time. It would be very exhausting. However, with a robot, you can just leave it to do it by itself and you can relax in the meantime. So it saves a lot of time and effort on your part, and you can just use that time to do whatever you want to do while the robot is mowing the lawn for you. However, my project, the goal was to create an autonomous lawnmower which would be able to use GPS to guide itself. The lawnmowers on the market currently use a physical boundary wire to mark off where it can and cannot go. So basically, it uses a wire that you stake into the ground wherever you do not want it to go, such as the edges of your lawn or a flower bed or a tree, and you just circle around it and make sure that it doesn't go there. However, I want to create a robot that would only use GPS to guide itself within the lawn without using any physical wires. So the first part of this project was to build the chassis itself. So this would include the frame of the robot as well as the main board that would control the robot and other attachments such as the motor controller, GPS, and the motors itself. So the second part of the project was to create a mapping program. So this mapping program was created using JavaScript, and it would be able to plot coordinates on a satellite map, such as Google Maps. So you basically can zoom in on any lawn, be it your own or somebody else's, and you can click around the edges of the lawn and it will record those coordinates where you clicked, and it would basically create a virtual map using those coordinates that would be able to send to the navigation program to be used to control the robot. As for the navigation program, it was coded in C++, and it utilized GPS to direct the mower. So how it worked is that as the mower was moving, it would start in, say, one corner of the lawn, and as it moved forward, its GPS coordinate is constantly updating. So it constantly keeps track of its own GPS coordinate, and as it moves forward, when its own GPS coordinate matches up with that of the map, then it would automatically turn around and go back the other way until it hit the boundary again, and then it would keep going back and forth until it had mowed the entire lawn. Another part that needed to be coded was the user interface. So this was coded using Java, and what this interface would allow you to do is basically you can tell the robot when to go, where to mow in, and you can just tell it to start or stop at any time without actually having to physically interact with the robot. So you can use Bluetooth to connect with the robot to control it without having to power on the robot by hand. So for results, the actual physical chassis was able to be assembled successfully. So this included the tires as well as the frame of the chassis itself and all the supports within, as well as the wheels. And as you can see in the picture in the bottom left, there is a small disc at the bottom of the mower. So this disc is where the blades would be attached to actually mow the lawn. So for this robot, there are 3 motors. So 2 of those motors control the left and the right wheel, respectively, and they control how fast they spin. So they basically control the direction and the speed at which the robot moves. However, the third one, it only spins the disc that has the blades onto it. So it spins the blade to allow the robot to cut any grass that is beneath it. So as you can see in the middle picture, there are two batteries connected to the robot. These are two 12-volt LiPo batteries. So the robot needs 24 volts in total. And these are connected directly to the main board, which moves the power over to the two motors, the three motors, as well as any other sensors that need that power. And of course, it powers itself, which controls the movement of the robot. So an obstacle that came up during this project was the PCB, or the power control board, which is basically the brain of the robot. It tells it where to go and when to start moving and all that. So the troubleshooting for this was a major obstacle, since all the parts of the PCB needed to be soldered on individually. So all of the connection to the different sensors, such as GPS and the sonar sensors, as well as the motors and the motor encoders, all needed to be soldered on individually. So a problem that arose was that when the PCB was powered, the motor controllers on it were unable to receive any of that power, and therefore were unable to tell the motors when to start. So this was a problem that came up, and it was solved when the emergency switch was connected to it. So it turned out the emergency switch was what was blocking the power from getting to the controllers. However, it could have been any number of issues, such as a blown fuse or simply a connection not being soldered on correctly. But fortunately, it was just the emergency switch that was the issue. For the mapping program, this mapping program was able to effectively create a map and then store the coordinates of this map. So as you can see in the picture, there is a simple rectangle drawn out. So it recorded the 4 corners of that rectangle, and it recorded those coordinates and was able to send it over to the navigation program. So the mapping program is able to map out an entire lawn. However, for this test, I only created a simple rectangle for simplicity. So the navigation program was able to direct the robot to move within this simple rectangle without it crossing any of the boundaries, and it was able to it was able to cover the entire area of the rectangle, and it was able to mow all of the grass within. However, the accuracy of the GPS on the robot has an error of approximately 1 foot. This can change depending on weather conditions or the area in which it is mowing, if there's any buildings, say, blocking the signal of the GPS. However, normally it has an error of around 1 foot. And without accounting for this error, the robot can move outside of the boundaries that were set up by the mapping program, since it thinks its own coordinates are still within the boundaries when its actual position is outside of it. So in the code, there needed to be some padding added to account for this error, and some calculations need to be made to account for this error so that it would be able to stay within the boundaries even with the error of the GPS. However, once these solutions were implemented, it was able to effectively stay within the boundaries without going outside of them. So this is a video of my robot in action. So as you can see, it starts in one corner and it moves forwards until it hits the boundaries, and it will turn around 180 degrees and come back. So it mows in lanes very similar to how a human would mow. However, those robots on the market currently that use physical wires, the robot basically moves forward until it hits one of those wires and it senses that wire, and then it will turn at a random angle and keep mowing until it hits another wire. However, this is very inefficient. It will eventually mow the entire lawn. However, it is very inefficient, unlike my robot. So as for conclusions, the assembly of all the parts of the robot, including the frame of the chassis, as well as all the electronic parts inside to control the robot and the motors, was successful. And the mapping program was able to generate these coordinates and create a virtual map that effectively represented the boundaries of the yard that I was trying to map out. And it was able to send this virtual map over to the navigation system on the robot. And this navigation system was able to effectively guide the robot using only GPS to stay within this generated map. For future research, I would like to be able to create an app that would allow you to more easily create GPS boundaries. So what it would be able to do is that you can just walk around the edge of your yard, and once you walked around your entire yard, it would automatically create the GPS map of your yard. Instead of having to do it within the mapping program, you can just use your app and walk around to create those maps. Another thing I would like to be able to do is create an algorithm to direct the robot more effectively. So as you can see in this picture, say if there were two obstacles in the middle of your yard, such as two flower beds or two trees or whatever it may be, it would split the yard into two quadrants or zones basically, and it would start in one zone and it would mow the entire thing, similar to how it is currently doing right now by just tracking its own GPS coordinates. And then once it reached the end of the first zone, it would move into the second zone and start mowing again in order to effectively and efficiently cover the entire area of the yard. With the current navigation system, it would only be able to cover part of the yard, since whenever it hit the obstacle, it would just turn around and go until it hit the edge of the yard again. So it would miss part of the area that is under the obstacle basically. So if it would hit the obstacle and it would miss the part under the obstacle where it not be able to mow, and it would just keep going without noticing that it missed that part. However, with this new algorithm, it would be able to mow the entire yard. And some other things I would like to be able to do in the future is create some boundaries around trees or obstacles, such as trees or flower beds, whatever it may be. So in the picture, you can see this is the current mapping program, and this mapping program is able to cover the entire yard. However, it is not able to account for all the trees and other obstacles within the yard. So in the future, I'd like to be able to basically cut out the trees from the map and create circles around it that disallow the robot from going into that area and colliding with those trees or other obstacles. Another thing I would like to be able to implement is the use of sensors, such as sonar sensors, to detect unexpected obstacles, such as animals or humans or whatever it may be. So how it would work is, say the robot is mowing and then a dog or whatever animal runs in front of it, and it would use the sonar sensors on board. So these sensors work by throwing out sound, and then once the sound waves hit something, it reflects back and it records the amount of time it takes, and it calculates how far away that object is from it using the amount of time it took for the sound wave to come back to it. So this sonar sensor on the front of it is constantly detecting things in front of it, and if something comes sufficiently close enough to it that it did not expect to be there, it would automatically stop and wait for that object to move out of the way for it to continue to moving. So if the dog runs out in front of the mower too close to it, it would automatically stop to make sure that it doesn't run into the dog, and then it would start going once the dog had moved out of the way and would continue on its original path. So I'd like to thank my mentor, Robert McGillivray, I'd like to thank Newton's Attic for letting me research at their location. I'd like to thank Karen Young and the KYRP research program. And I'd like to thank my friends and family most for their support during this time. These are my references, and are there any questions?